We are at hash tables, and I'm starting right out of the gate with a let's go because this is going to be fun. Starting with some terminology. What is a table? It is an abstract data type that's going to store and retrieve records, usually based off of some type of a key, an ID, a social security number. A key could even be a combination of like a first and a last name. What is a record? A record is going to be an individual row into that table. So if we have a database of student records, each record in that database, in that table, will contain all of the information for a particular student. So here's a sample table. We have all of these records in this table. We have Betty here with ID 0033333. And apparently this table was storing some scores, and Betty scored a 90. Pretty straightforward example of this abstract data type. Now it's called a table because we want to talk about, or it's an abstract data type, and we want to talk about how we can implement this abstract data type. So here, consider this problem. We want to store 1,000 such student records into this table, and we want to be able to store them based off of their ID number, and then search them based off of their ID number, and delete them based off of their ID number. Given this table, knowing that we want to search, add records, delete records, and we want to do this in the most efficient way possible, what data structure is most appropriate? The answer is a hash table. But prior to learning about hash tables, since this is an abstract data type, that means we want to understand the goals, the behaviors, and what we're left with now is how we would choose to implement this hash table. What if we used an array to store the records in unsorted order? That would be a way of creating this table. It could be in a two-dimensional array or a one-dimensional array of objects. But if you have an unsorted array, consider the running time. Pause the video and think about what would be the running time to add a new record. Well, if the array is unsorted, you could simply add the record at the next available spot in the array. This would be O of 1. If we had 423 values in the array currently, from index 0 to index 422, the next value clearly goes at index 423. So keep a count, add it at the next spot, that's O of 1. What about deleting a record from this array? Well, it's unsorted. So what happens is we need to first of all go find it, which we need to loop over the entirety of the array perhaps, or at least over the n values in the array. That's an O of n search, looping over, trying to identify, are you the one we want to delete? Are you the one we want to delete? And when we finally find that person we want to delete, well, we're going to delete them, but now we're going to have a hole in the array. How do we fix that hole? You could think, well, I need to shift everything back, but actually you can do a slight improvement on that. Since it's not sorted, you could really just take the person who's at the end of the array and you can put them into that hole position, which would happen in O of 1 time. But in the end, we're still left with this O of n search to find the person that we would like to delete. Now, searching for a record is also, again, just O of n. Why? Because it's unsorted. So now what if you want to use an array, but it's now a sorted array? And the whole goal is to implement this table of records. We would like to use a sorted array. What would be the running time to add a record? Well, I'll tell you, you need to find the correct insertion position. And you could do an O of n loop to find out where that correct position is. But in fact, you could do a play on binary search. We're not searching, we're searching for the insertion position, not for a node that exists. But there's a way that you could do a play on binary search where you can get O of log n to find the new insertion position. So that would be fast, that would be nice. But even then, what's going to happen? After you find that insertion position, what needs to happen is you need to shift all of the other items over one position to the right, and ultimately it's going to be O of n. What about deleting a record? Well, deleting a record, you need to find that record to delete here, and then you need to, after you find it, you need to shift everything back to fill the hole. And so ultimately it's going to be O of n, but finding the record here, that's actually O of log n to actually find the record that we want to delete. Through the power of pause, that has now been fixed. It is O of log n to find the record we want to delete because we have a sorted array. Of course, we can search this in log n time, but even after we find that record you want to delete, What needs to happen? Shifting everything back to fill that hole. We can no longer move the item at the end into that position because the array is sorted. Searching for record, we've already gone through that. Binary search, O of login, super fast. We could also go through what if we use a linked list, a sorted linked list, an unsorted linked list. Ultimately, you're going to have a lot of these you're going to have some logins, not even on a linked list though, because we don't have any searching. You're going to have a lot of O of n's. There's going to be some times where we can use a linked list and get an O of 1. Let me ask you, if we have an unsorted linked list, what is the running time to insert a new value? And the answer is O of 1. You can insert right at the front. If you have a tail, you can insert right at the end. That's super fast. Beautiful. But now what is the running time to delete an item from that linked list? It would be O of n, because you now need to go search for a particular item. So there's the pros and cons of each of these. Ultimately, what if we now used a binary search, one of our newer structures, a binary search tree, to store these records? What would be the running time to search a binary search tree, or to add values into that binary search tree, or to remove values? Now we know that the running time of binary search tree, worst case big O, is O of n, but I've said that I want you to remember in your heart of hearts, connect the idea of log n to a binary search tree, because that's really the goal of a binary search tree, to split that search space in half, even when you're inserting insert to the left or insert to the right. But big O, worst case scenario, if we have a skewed tree, that's a problem. But let's assume best case scenario, that we can insert into this tree in O of log n time. You see that asterisk here because the assumption is that we're going to have a perfectly balanced tree. So we can even delete from this tree in O of log n time, and of course we can search it in O of log n time, all with the assumption that the tree is balanced. Log n, huge improvement over n. If n is a billion, log n is 30, huge improvement. So that would seem to be the best solution, but it turns out there is something that is so much faster than even log n. We're going to look at today how we can insert, how we can delete, how we can search, not in O of n time, not in O of log n time, but in O of 1 time. And in fact, the solution we're going to look at is the most simplistic solution. It's a solution that you could have come up with before even taking this course on data structures. And what is that solution? Just use an array. You're like, wait, what? Didn't you just tell me that using an array is going to be O of n to use an array when I want to possibly insert or delete? How can using an array give us O of 1 for adding, for insertion, for deletion, and for searching? It's a special type of an array. Specifically, it's an array that is so large that every record will have its own unique spot in the array. And we call this array a direct access table. So going back to that example where we have Andy, Betty, David, Bill, what if we make the array so large that their index, they're stored at the index that matches their social security number? So Betty is at 334561894. That's Betty's index. No one else has that social security number. So we can directly access Betty in O of 1 time, print that information of Betty, print their information, access their information, update their information. So here we have this table based off of social security numbers, and we have this huge table. How large does it have to be? Well, think about how many digits are in a social security number. There are 9 digits in a social security number. So if you have 9 digits, that would go from index 0 all the way to index 999,999,999. That would be a billion size, an array of size billion addresses, references, where each reference points to an object. So if you make an array that is that large, each person has a guarantee to have their unique spot in the array. Super fast, O of 1 for insertion, O of 1 for deletion, O of 1 for searching. Fantastic. We should like QED in the course. We have found the best data structure, period. What's the problem? So it's way fast, but what is the, I wrote here, huge problem? If you want to say, for example, you want to store 1,000 students based off of their social security number, well, if a social is 9 digits, that's going to be an array of size billion we just mentioned. So we would use an array of size 1 billion to store a whopping 1,000 students. So we end up with direct access, O of 1, in speed, but I say here we have O of not cool in memory, right? We end up having an array of size billion to store 1,000 people. That's a fail. That's a problem, but what's the but? But we got O of 1 insertion, O of 1 deletion, O of 1 access and searching. So we need a better solution. We want constant time for adding, for deleting, for searching, but we also want a reasonably sized array. Like, we're pretty picky here, right? My goodness, we want fast speed. We also want a reasonably sized array. Ideally, what we want, if I want to store 1,000 students, I like an array of around 1,000, maybe 2,000, maybe 5,000, not a billion. We don't want to waste all of that extra space, but we still want that direct access that gave us this O of 1 lookup time. So I see here we're pretty selfish, right? We want O of 1 time, we want limited space. How can we do that knowing that it was that huge amount of space that really facilitated this direct access, because now everyone had their guaranteed unique spot in the array. What we ideally want is something like this. Here we have an array of size 1,000, and we're going to place students into this array based off of their ID number. And what we need is a way to map a social security number to an index. So Betty here, who apparently got a new social, Betty here with social 527447521, Betty would map uniquely into index 368. So we would want this social to somehow map into index 368. If we could do that, and if we could guarantee somehow that Betty is the only one that will map into index 368, we will have accomplished our goal, right? We would have accomplished our goal. So I say here, let's look at a magic address calculator. We're going to build a make-believe function called this magic address calculator. The input to this function is a social security number using this example. It's going to be some key. And this function will convert that social security number, which has many digits, into a smaller number that will therefore be an index into a more reasonably sized array. Ideally, this function will have some type of guarantees that each social will map into its own unique index of this array. The function should operate in constant time. And so we want to make sure that this happens very quick, this conversion, that it's in constant time, and it does because it's some basic math. And we also want to make sure we're using a reasonably sized array. This is the basic idea of a hash table. So we saw a direct access table, which is not a hash table. A direct access table is this huge table of size billion to store maybe 1,000 students, maybe 30 students, which is worse. A hash table, take those same ideas. Now we want a smaller array, a smaller table, but we somehow want to guarantee or hope that each person maps into their own unique index of this table. Let's look at some terminology. The term for a hash table simply means it's an array of these values where each index of this array is going to be calculated using a hash function. How do we search in a hash table? So let's say you're searching for a particular student record with this key value. Instead of a social, maybe they each have an ID, and the ID is simply 4256. To find an item in the hash table, we do not use that standard protocol of searching the entire hash table from index 0 to the end, nor will we go directly to index 4256. Rather, we're going to take this key 4256, we're going to insert it into a hash function. That hash function is going to spit out a smaller version of that key, let's say 37. And then we're going to go to index 37 and hope to find the person that we are looking for. This is the overall idea. What is a hash function? The short answer, it's a mathematical calculation that maps a larger search key into a smaller number that can be a number or an index into a reasonably sized hash table. So this hash function can be super easy. It doesn't have to be some amazingly complex mathematical algorithm. It can be a super easy math function, and we're going to go over several of them. A hash function should be fast to calculate. It should be O of 1 to calculate this smaller index into this reasonably sized table. The hash function should also, in theory, be sophisticated enough where it distributes items pretty consistently or evenly throughout the table. You don't want to get a situation where you take these large social security numbers, ID numbers of the students, of the records in the table, and they all end up hashing to the same index. That would be a disaster because you can't store all those people at the same index for what we've seen thus far. What is hashing? Hashing is simply the way to access a table in a relatively quick or constant time. We're going to use a hash function to determine this smaller index into a reasonably sized hash table. And we're going to also have to use what is called a collision resolution scheme, which we'll go over. But first, an example. Let's say we have a system for storing student records. We could store all of the records with the name, the address, the telephone number, and we're going to use the social security number of these students as the search key. Of course, as mentioned, we could use the entire social security number as their index, but that would require what? An array of size billion. That would be an epic waste. So that would be a problem. In our case, what if we only want to store 2,500 or 3,000 or even 5,000 students, for example? We don't need an array of size 1 billion to store 2,500 spots. Epic waste. However, what's the value? Let's understand the value though. If we use an array of size 1 billion, we would have a guarantee that each person has their unique index. Make sure we get that clearly. Also, that means, as a consequence, we have a guarantee that there would be no collisions whatsoever. What is a collision? A collision is where two or more records map into the exact same index of the hash table. So the good news is that with this array of size 1 billion, everyone would be guaranteed to have their own unique spot in the table, no collisions. Of course, the problem, what a disaster, epic waste of space, huge waste, size billion array to only store 1,000 actual students. So better to use the last 4 digits of the social security number. For example, if we had Betty, again, 589475127, instead of storing Betty at that entire index requiring a hash table of size 1 billion, what if we stored Betty at index 5127? So now we only need a hash table that goes from 0, index 0000, you can think of 4 zeros, index 0, all the way up to 9999. That would be a table of size 10,000, still larger than 2,500 or 3,000 or 5,000 students, but much better than a billion, right? So now Betty, instead of being stored at the index of her social, she would be stored at the index that comes from the last 4 digits of her social. So the size of the table is now much smaller, and we could still, hopefully, that's the key word, store Betty at a somewhat unique example, a unique index. This is the idea of a hash table. The problem, you can almost be sure there will be collisions. Look at these 2 sample social security numbers. The last 4 digits of both of them are identical, meaning that Betty and whoever this is would end up mapping into the exact same index of that array, of that hash table. That is a collision. That is clearly a problem and something that we need to be addressed, because you can't store 2 people at the exact same address, we need to have a way of handling those collisions, and we'll talk about that in just a bit. And here we are just a bit later, which is the next day. Let's continue now and talk a bit more about hash functions. A hash function is written h of x equals I. What does that mean? H is the name of the hash function. X is the key that we're going to be inputting into that hash function, and I is going to be that result that it's going to spit out to us and give us, which will be an index into this reasonably sized array. So if we're trying to add a new record to our hash table, once we calculate I, this smaller index, then we can use that index to then go save our record into this hash table at index I. Remembering that hash table here is simply just an array. So let's go over an example. We have a student with this particular social 589475127. We're going to take that social and we're going to input it into a hash function. This can literally be a few lines of code, its own method, another language, its own function, and that function is going to spit out a smaller version of that key. How? You could use some special math. We're going to go through some different options. If you look here, this particular hash function is only returning the last 4 digits of that key. Mathematically, that means we're simply dividing by 10,000 and getting the remainder. So we're modding this number by 10,000. The remainder is 5127. The hash function is simply, on this example, a one-liner. Return the parameter mod 10,000, and it gives you 5127. So now we can take a user's information, we can make an object out of it, and we can store that information of that user with this social, with all their name, phone number, email address, what have you, and we can store it at index 5127 of the hash table. So this hash function was super easy, simply taking the last 4 digits of their social and using that last 4 digits as the index into this reasonably sized array. So hash functions can really be as easy or as complicated as you want them to be. We're going to look at 3 basic types of hash functions: selecting digits, folding, and then using modular arithmetic. And these are just examples with the goal of what? Taking some large key, some key that would be so large that if we used it as a unique index into this array, we're going to end up with this direct access table with maybe a billion size of entries to store 2,000 people, which is a disaster. The goal is, given this key, we want to make a smaller version of that key to have a reasonably sized array, right? This is the idea, and we're going to then use that key to store information at that particular index or to search at that index for a particular user and what have you. So the first option is selecting digits. So instead of using the whole integer, we only select a particular set of those integers, maybe the last 4, the last 3, the first 5, right? So given this particular ID, just use the first 3 digits. Mathematically, you could figure out how to make that happen. That's pretty much what we did. Using the last 3 digits ends up being a bit easier because that is just mod. You can say mod that by 1,000. That remainder, 123, will give you those last 3 digits. This is super fast to calculate. It's easy to code up, but we normally won't get a random distribution of these items in the hash table. And think about that. If you have a hash table here, that would have to be 1,000 large, right? Because if you have possibly remainders from index 0 up to 999, so your hash table would be size 1,000, you want those to distribute rather evenly throughout the hash table. And it could be the case that this won't distribute evenly depending on how these original ID numbers are created, but you're going to end up having many people that will hash after the hash function. They're going to hash both into the exact same index, and we have that collision, which is a problem. Another type of hash function is called folding, where we can add the digits of the integer together. So for example, given this 9-digit ID number, what if we said, let's actually just add all of the digits together and we get 45. Let that be the result of your hash function. And now if I ask you, here's a good question to consider. If I said this was the hash function, how large of an array would you possibly need? Pause the video, think about how you could come up with that. If I'm trying to add 9 values together, how large of an array would I need to store all possible situations, all possible numbers where I'm adding 9 values? So the smallest would be if everything was a 0. What would the largest be? If everything was a 9. If everything was a 9, 9 plus 9 plus 9, 9 times would be 81. So you actually need an array of size 82 from index 0 all the way to index 81, including 81. And so that would be appropriate if you need to store maybe 50 students, 30 students, or what have you. This is just one particular way of holding, of adding those digits together. What if I said, take the first 3 digits, add it to the next 3 digits, and add it to the last 3 digits? We get this number, 1368. And now we can use that number, 1368, as our index into a more reasonably sized array. And a great follow-up would be, what is the possible range of indices using this type of folding? Well, the first index would be index 0. And what would be the last index that we would need in our array? Well, worst scenario, if this was 999 plus 999 plus 999, we would actually get 2997. So we would have to have an index from index 0 up to 2997. So therefore, 2,998 entries into our hash table. We could also use mod. Mod is probably one of the better uses here to come up with a great hash function. If you just take your key and you mod it by the table size, and it's been proven that when we use a prime number as our table size, we will reduce collisions. So for example, if you have a table size of 31, you only have 31 students, simply take that key, mod it by 31, you get 2 as the remainder, right? So if you divide by 31, 2 would be your remainder, and we use 2 now as our index into this hash table. What's the range of possible indices here? That's a good question. Make sure we're okay. If I mod by 31, what is the range of possible indices, right? Make sure that we're okay on answering this one. Consider that we're modding by 31. What is the possible set of answers that you will get? Well, the remainder could be 0. It could be 1, 2, 3. It could be up to 30. You won't have a remainder of 31 because then you could have had another whole number. But the remainder will be from 0 to 30 when you mod by 31. It should be an easy question, but it's always funny to ask. What are the possible set of answers if you mod by 12? Well, there should be 12 answers from 0 to 11. If you mod by 100, you should have 100 possible answers as a remainder from 0 to 99. So when you mod by 31, you're going to get 31 possible remainders. What are those remainders? From 0 to 30. And you're going to use those values from 0 to 30 as the indices into your hash table, your reasonably sized array. So hash functions also, they really only need to be designed to operate on integers as the key. Because you might be thinking, well, what if my key is a first name, a last name, a combination of those, or some other string? No problem, because we can easily convert strings into integers. And then from there, you can use that converted integer as the key to your hash function. I'm going to very briefly go over this. Not something we need to cover because everyone can come up with their own unique way, if you had to, of converting a string to an integer. What if we just want to assign the values A through Z to 0 to 25, then add those values together? That would work. You could use the ASCII or the Unicode of each character, add those together. Frankly, you could even use the binary, right, for the ASCII or Unicode and concatenate and do some other funny things. Long story short, many ways you can convert a string into an integer and then use that integer as a key to your hash function. So ABC could be 0, 1 plus 3, 0 plus 1 plus 2, or it could be 65 plus 66 plus 67 if you're going to use the ASCII values. Or it could be this. You can come up with so many different options. Question: what is a perfect hash function? What would be considered a perfect hash function? Pause the video and reflect just for 1 minute and spend a minute. What could be considered a perfect hash function? The ideal that we are looking for. Pause the video, come up with that answer. Spend a minute. Perfect hash function. The ideal situation in the perfect hash function is one that will perfectly, uniformly distribute all of our search keys to unique indices within the hash table. So if all of the telephone numbers all somehow mapped into different indices, that is the ideal, that is the perfect hash function, and that does not exist. So realistically, we will encounter collisions. And remember that collision is when you have this hash function and it maps two keys into the exact same index of the hash table. So if we insert key 1 right here into the hash function, we insert key 2 into the hash function, both of those records end up having the exact same output from the hash function. Therefore, we're trying to really save two records at the same index. That is a problem. What remains in this video is to talk about collisions and various collision resolution schemes, how we really deal with those collisions. So we want to store student records based on a small class of 30 students, and we want to use their student ID. Assume the student ID has 7 digits, so we could have this direct access table of 10 million in size, which would be a disaster, a waste of space. Instead, we're going to make an array of size 31. So our hash function is going to be simply modding our key by 31, a very basic hash function. And we understand that now very clearly. When we mod by 31, we're going to get 31 possible remainders from 0 up to 30. We have 31 students. We're going to have 31 spots in our array, our hash table. It's perfect. But, what's the but? Realistically, you're going to get collisions. When I take this person and I divide by 31 and I look at the remainder and I do the same thing for this person's student ID number, they both hash into index 21. That is a collision. That is a problem. We're trying to store two students at the exact same index. Clearly can't happen. Our interlude, when you copy a snippet from Stack Overflow and it doesn't work, those bastards lied to me, which they did. Okay. I have to warn you, this one is painful. So as you've seen in a couple of videos, I love my alma mater, but we had some disastrous bike fails where students kept locking bikes to 4-foot posts, which is a disaster because we were getting emails as students saying, hey, bikes are being stolen around campus, heads up, make sure you lock them. And, as I'm teaching, we have 300 students, we're all laughing. It's like, no. They're just literally walking away because they're lifting the bike off of the post, right? So the UCF police, they realized that we had some challenging students, and the idea of having these posts around in front of the student union was causing some problems. So they decided, instead of just having these vertical posts, right? Instead, they put the traditional bike lock type of systems, right? Where you see these not posts, but now it's these things that go like this, where you put your wheel into it and you put your lock around it so you can't just lift up the bike and walk away, right? I warn you, brain cells can and will be lost by looking at this picture. So here's what we have. It hurts, but that actually happened. And one of the students, they saw it, they said they cried, they snapped a photo and they sent it. How fantastic, incredible. All right, so collision resolution schemes. When we have a collision, we need to fix it. That's what these schemes really are. It's a process that's going to assign these search keys that are spit out from the same hash function to different locations in the hash table, so hopefully everyone can find their own unique location. So whenever possible, we do want the hash function to distribute these search keys as uniquely as possible, as evenly as possible within the table to avoid collisions, but they can't always be avoided, so we need to deal with these collision resolution schemes. We're going to discuss a variety of approaches. The main two overall approaches are open addressing, and this is basically where we're going to reassign an index, a key to some other index in the hash table, and then we have restructuring the hash table. We have bucket hashing and separate chaining. We're going to cover all of them. Now, open addressing is where we said maybe a person is hashed into index 8, but someone's already at index 8. So now we're just going to find another location in the hash table to put this person. Index 8 didn't work. Let's try index 9, then 10, then 11. That's actually one of the approaches. Another approach is not try 9, 10, 11. It'll try 9, then it'll try maybe 12, then it'll try 17, and so on. We're going to go through these different approaches. That's the idea of open addressing. So the general approach is simply probe or look for some other index in the table. What remains is the probing sequence. Which indices do we ultimately look at and examine to try to find some open index in the hash table? The three types of probing are linear probing, quadratic probing, and double hashing, and we need to understand each one of these. Linear probing, super straightforward. If you have a collision at a particular index, simply look at the next index. You got a collision there? Look at the next one. Collision there? Look at the next one. Keep doing this. Even wrap around the array and go back to index 0 until you find an open location. So if table I is occupied, look at table I plus 1, then table I plus 2, table I plus 3, and so on. Important to know is that when you use this scheme, you actually need 3 states of the table: empty, occupied, and deleted. And try to think about why you might need those states. I'm just simply planting that seed. We'll cover that briefly of why we need them. Just planting that though. We're going to need 3 states for every single index to know, is this index currently empty? Is it currently occupied? Or was it occupied, but now something has been deleted from this index? And we'll talk about why that's necessary. But a common problem with linear probing is we have elements that end up clustering together. Nodes or items end up clustering together in that hash table, which might make sense. If you have a bad hash function and many elements are all hashing to index 5, well, the first one's going to go at 5, the next one will go at 6, the next one will go at 7, the next one will end up going at 8. And what if the hash table is size 100? So you're going to get many nodes or items in this hash table that really all are clustered together around index 5. So let's go through an example. We have this table size of 31. Our hash function will therefore be the key mod 31. Divide by 31, get the remainder. Let's look at what happens on a series of inserting new keys into this hash table, or new students, if you will, based off of their ID into this hash table. So here's the first student with this ID or this key 1, 2, 3, 4. They hash into index 25, no problem. We put them at index 25 of our array, and I'm just calling the array table. So what do we put at index 25? We're simply storing their key. I could have stored an entire object, a node, an address, but you get the idea. For the purpose of this example and this visual, we're simply going to store their key at index 25. Next person, by design, the key used immediately causes a collision. If you take 4055, if you divide it by 31, you're going to get a remainder of 25. Well, we can't put 4055 at index 25 because we already have 1, 2, 3, 4 at index 25. So what do? We simply put them at the next index, which is index 26, and that's where 4055 goes. The next person, also by design of the example, I had them cause a collision, and they hashed also into index 25. We can't store them at 25. We cannot store them at 26, so we store them at 27. Person 3962 goes at index 27. The next person also causes a collision, and they try to go at index 25. Person 5853 can't go at 25, 26, or 27. They go at index 28. The next person hashes to index 30. No one's at index 30. So we simply save them directly into index 30. The next person, they also hash into index 30. When you divide 1270 by 31, you're going to get 30. And clearly we can't store them at index 30 because someone's already there. So now we check index 30 plus 1. Well, there is no index 31, but you have to now use mod again, and it wraps around. And so now we're going to index 0, and we save person 1270 at index 0. All other entries into the table are empty. That's it. Hopefully we're okay with that. I went through that at a normal speed, not slow, not fast. You can rewind, watch again. But that's the idea of saving values into our hash table and using this linear probing collision resolution scheme to deal with whenever we have collisions. So I mentioned that you need to have an empty, occupied, or deleted state saved for every single cell. Why might that be? Why is that so important? So imagine if we wanted to delete record 3962 on this previous example. So here we have record 3962. Imagine we deleted that person from the hash table. So now index 27 is available, right? It's available, it's empty. Like if we didn't have a state, we would just know no one's at index 27 and we can save someone there. So imagine if later, after deleting person 3962, so this index 27 is available, imagine that we're looking for index, or we're looking for person 5853 in the hash table. How would that work? And I could have maybe given this example first, so I'll back up and give that example, and we'll talk about, and you'll see why it would be a problem without the state. Let's pretend we haven't deleted person 3962. Everyone is in this table. How do we go about looking for index, or for person 3962, for example? Well, we're going to take, if I'm looking, we're doing a search now, not saving, we're doing a search for 3962. I'm going to throw 3962 in the hash function. It's going to spit out 25. I'm going to look at index 25 and I'm going to say, are you 3962? It says nope. Am I going to stop the search? No, because I know that we used linear probing. So maybe person 3962 got inserted at index 26. So I'm going to check, hey, index 26, are you 3962? Nope. Do I stop the search? No. So I'm going to check index 27. Are you 3962? And the answer is yes, I am 3962. And so we found the person, we print them, we edit them, we do whatever we need. Same thing if we were looking for 5853. I would start here, go to index 25. Are you 5853? No. Go to index 26. Are you? No. Index 27. Are you 5853? No. Index 28. Are you 5853? No. Done. One more time. What if I was looking for some other number? Not these four numbers, but some other number, let's just call it 5555. Just pretend that number hashes to index 25. How would that work? We'd say, hey, index 25, are you 5555? No. Index 26, are you 5555? No. Index 27, what about you? No. Index 27, do you have something? Index 28, do you have something in your index? Yes, we do. Are you 555? No. Index 29, do you have something at your index? 29 says, nope, I don't have anything. So we stop our search, because at that point, if 5555 was in the array, it would have been at index 29, right? Because since 29 is empty, we know that probing sequence had completed. So now one more time, if we had deleted 3962, check this out. If we had deleted 3962, and now we're searching for 5853, what would happen? 5853, it hashes to index 25. So we're going to go to index 25. We're going to say, are you 5853? Nope. We go here to index 26. Are you 5853? Nope. Index 27 says, I'm empty. So we would stop our search, even though we know from the example that we just built, 5853 comes next. But we would have stopped our search. So that's a problem, which means we need to use this empty, occupied, and deleted states. At the very beginning, the state of every single cell would be empty. And then every time you save something at an index, you're going to change that state to occupied. But when you delete an index, you change that state to deleted, which tells you, oh, something was there, it was deleted, so let me continue that probing sequence. So here, using the same example now, if we're looking for 5853 and we come to index 25, because that's where it hashes at, are you 5853? It says no. 26, are you 5853? No. 27 says, hey, I've been deleted, so maybe you need to keep searching. So we say, okay, great, nothing's at 27, but we're going to now go to index 28. Are you 5853? And we find it and we're done. Or if we were looking for that 5555, we would have not found it in these first four, but then we go to index 29, and 29 says, hey, I'm empty. No one was ever here. You should stop your probing sequence. That's the idea of why we need those three states, and that's linear probing. Quadratic probing, pretty similar. The only difference, instead of checking the next index one by one by one, you simply check the index based off a sequence of squares. If table I is occupied, we're going to check table I plus 1 squared, which is really table plus I plus 1. But if table I plus 1 squared is occupied, we check table I plus 2 squared. Then table I plus 3 squared. Let's think about that. If index 10 is occupied, we check index 11, which is 10 plus 1 squared. But if index 11 is occupied, what do we check next? We're going to check 10 plus 2 squared, index 14. If that's occupied, we're going to check index 19, 10 plus 3 squared, index 19, and so on. So the only difference between these probing, these open addressing collision resolution schemes, from linear probing to quadratic probing, even to double hashing coming up, is really just the step size of, once we see that we have another collision, it's still occupied, which is the probing sequence, what index do I check next? Linear, just the one right after each one, after the next. You're at 13, check 14, 14, check 15. Quadratic probing says no, check based off of a sequence of squares. We have some clustering still, but it's less. Very quickly, we can go through the same exact example, same numbers. We already know how they work. 25 hashes to 25, we save, or 1, 2, 3, 4, it gets saved at index 25. 4055 hashes to that same number. It gets saved at not 25 because it's not available. So we save it at 25 plus 1 squared at 26. Now, 3962 also hashes to 25. So we check 25 plus 1 squared, which is 26. That's unavailable. We then check 25 plus 2 squared, 25 plus 4, index 29. That is available. What about this next one? 5853 goes to 25. It's not available. We check 25 plus 1 squared, 26. It's not available. We check 25 plus 2 squared at index 29. Someone's already there. Then we check 25 plus 3 squared, 25 plus 9, wrapping around, bringing us to index 3. It is available, index 3, so we save 5853 at index 3. That's really it. If you get that, the rest of the example is now going to make sense. All other entries in this table are empty. Pretty easy to understand quadratic probing once you already fully get linear probing. And now we have double hashing, also easy. Here I'm going to tell you we use 2 hash functions. The first hash function works as we've already seen, determining your index into this hash table. But if you have a collision, we use the second hash function to do what? To determine our step size of the probing. So some restrictions, we need to make sure that that second hash function, when we put a search key into it, we can't get 0. That would be a disaster. What does that mean? Because if the purpose of the second hash function is to determine your step size, think about if we got 0 as a step size, meaning we hash initially with our search key into index 25. And there's a collision. So what do we do now? We put it to the second hash function. It says, take a step size of 0. So now we go right back to index 25, a collision. Right back to 25 again, a collision, because our step size is 0. What a disaster. That's a problem. Don't let that happen. You also don't want the 2 hash functions to end up returning the same values, because again, we're going to be having more clustering if that occurred. So let's go over an example. Got the same numbers, same table size of 31, same initial hash function of key mod 31. Here's a second hash function, 23 minus key mod 23. I could have used 17 minus key mod 17. We're just really trying to get an appropriate step size. If you think about this mathematically, given some key mod it by 23, the results are going to be from 0 to 22. So the step size is going to be either 23 minus 0, so a step size of 23 over this table, or 23 minus 22, a step size of 1. So that's a big range of step sizes, but that's okay. So let's go through this. This first person, they hash into index 25. We save them, of course, at index 25. This next person, they hash into index 25. It's a collision. So do we check 26? No. We do what? We take their key and we throw it into the second hash function, and it gives us 16. What do we do with that 16? That's our step size, meaning we're going to start at the initial index that we hashed into, 25, and from there we're going to take a step size of 16 to check. Now, when we take 25 plus 16, we arrive at index 10. No one is there. That is where we save the key 4055. Do the next one. 3962 hashes into 25. We, of course, get a collision. So we use their key and we throw it into the second hash function, and we get 17, which we'll use now as the step size. So we start at index 25, we add 17 to 25, and that will bring us to index 11, which is available. Notice we have far less clustering. We're at 11 and far less collisions as well, and we save 3962 into 11. What about this next person, 5853? They also, of course, hashed at 25 by design of the problem. And then when we take 5853, therefore, and we put it into the second hash function, we get our step size of 12. 25 plus 12 brings us to the table at index 6, where we put our key, and then we had 2 more. So this is the overall idea of using double hashing, just yet another probing sequence. So here, important to see, what if I said h1 with some key, and our hash function is key mod 13, and here, if we took our key and we put it into a second hash function, which was 11 minus, for example, key mod 11. So if the key was 30, check this out. If the key was 30, this would be our probing sequence. So our probing sequence, when you put 30 into this, if you take 30 divided by 11, and you get your remainder, what is 30 divided by 11? It's going to be 2. You're going to have a remainder, right? 30 divided by 11 is going to be 2. 2 times 11 is 22. 30 minus 22 is 8. 11 minus 8 is going to be 3, and that is your step size. So 30 mod 13, we're going to hash right into index 4. Let's say there was a collision, so the step size is 3. So then we check index 7, then 10, then 0. Why 0? Because we said only a hash table of size 13. So now then 0, then 3, then 6, then 9, then 12, then 2, then 5, then 8, then 11, then 1. And the next index we check, you can see what's 1 plus 3 would be 4, and we'd be starting the sequence again. And so a takeaway here, what if the key was 50? Here would be our probe sequence. And so it's important to know that if the table size is prime, the probe sequence will visit all indices of your table. That's a big deal, because we want to make sure that we're trying to distribute items as evenly as possible. If your table size is prime, your second hash function designed well will visit all indices of the table. And so with open addressing, of course, increasing that table size will reduce collisions. When you increase your table size, though, of course, you're using more and more memory. What are the other two options? Restructuring the hash table. This is the second type of collision resolution scheme. How is a hash table restructured for collision resolution? We're actually going to change the structure where multiple keys, multiple nodes or objects can be stored at the exact same index. And if I were to ask you how you can make that happen, you'd probably think about exactly what we're about to be told. You can use arrays, or we can use linked lists. Arrays or bucket hashing. Linked list is called separate chaining. Bucket hashing simply means that we're going to have at every index of our hash table, imagine a bucket. And anyone who hashes into that index, throw them in the bucket. Another person goes to index 25, throw them in that bucket as well. You're going to have a bucket that's going to store all of those people. In code, you're going to have a two-dimensional array. At every index of your hash table, you're really going to have an array of positions that can now store, an array of indices that can now store multiple people at that initial index. The problem with this is that choosing this bucket size can be challenging, because if you make that bucket size, that second dimension of the array, too large, you're back to wasting space. That's what we're trying to avoid in the first place. But if you make it too small, you're going to end up having collisions, because that bucket's going to fill up And now you have to then go back to one of those open addressing schemes where you're now doing linear probing, quadratic probing, or the double hashing. Here's our example, same numbers. See how easy this is. I can run through this one in 15 seconds. First one goes at 25.0. Next one goes at 25.1. Next person hashes at 25. We put them at 25.2, at 25.3. Pretty easy to understand how this bucket hashing example works. But now you can see how large should you make that second dimension. Here we have a table size of 31. So should we make that second dimension like size 5? So only 5 people are stored at every bucket. But now you're really taking 31 times 5. You basically have now 150 indices to store 31 people. That's a waste of space. So choosing that bucket size is problematic, which is of course why separate chaining is a common viable solution. Now, at every single index, we have this bucket, but the bucket can grow. The bucket can shrink. Because now we're going to put a linked list at every index of our hash table. So the size of that bucket is dynamic, right? So it's less problematic than that static bucket implementation. Here's our example. The first person, they go to index 25. Here they are. The next person who also goes to 25, we simply insert them at the front. Next person at index 25, insert them at the front, and so on. This is the idea of using a linked list at every index of the hash table. Now, if you had a horribly bad hash function and everybody, let's say you had a hash function where you have your key, your parameter, and you just say return 8. That's a pretty gangster hash function, meaning that no matter who you put into this hash function, it returns 8 and they need to get stored at index 8. Well, now, if you insert 1,000 people into this hash table, all 1,000 will be stored at index 8, and your linked list at index 8 will be 1,000 long. And so what should have been a fast data structure has now degenerated into basically an O of N linked list at index 8 of your hash table. What a disaster. So that's not realistic, but it is important to understand that even using this example, it's important to have a high quality hash function that can distribute items evenly using their keys into this hash table. Summary. We've made full circle, right? We started with arrays that had pros and cons. You had the shifting, you had O of N insertion and O of N deletion for sorted arrays. We then moved to linked lists to avoid that shifting. Linked lists have their own pros and cons. They're dynamic, but we still have O of N insertion, O of N deletion for sorted linked lists. We then studied binary search trees, which was like, whoa, it was an epiphany because now we had a dynamic data structure, if balanced, O of log n insertion, O of log n deletion, a really cool idea of embedding this super amazing fast thing called binary search into a dynamic data structure. Amazingly cool, but still O of n if the tree is skewed. So it's a O of n worst case scenario. But if it were balanced, O of log n, we then covered stacks, queues, heaps, but here we are now making full circle. It turns out that the fastest data structure that we're going to be using is an array, our baby. Let's go. When we use this array, this hash table, this modified version of our direct access table, we get O of 1 access into this table because as long as your hash function is pretty accurate and it's computed relatively fast in constant time, we're going to get O of 1 access into this table. We can hopefully minimize collisions, keeping that table to a reasonable size, not wasting space. And now we have our O of 1 speed using an array. That's awesome. Comparison of the implementations, our, I say slowest to quickest, or maybe least valuable to most valuable, linear probing, quadratic probing, double hashing, and then poor bucket chaining got thrown out because it's not as valuable. It helps us understand the idea of restructuring the hash table, but once you realize, wait, the problem of the bucket, how big do I make it? Do I make it too big, waste of space, too small, more collisions? You throw that one out and you're left with separate chaining. This is it. Hash tables, O of 1, incredible. What remains is now using them in practice. Was it momentous? You decide. 2 demotivators. The first one, from despair.com, A despair motivator. It is always darkest just before, ouch. You always say, oh, just before the sun comes out or the light starts shining or you have hope. No, it's always darkest just before it goes pitch black. Ouch. Underachievement because soaring with the eagles requires so much more effort. It has been fun. As always, feel free, leave a comment, ask questions. Take care, everyone.